We're now going to look at the last major type of reaction in this chapter, and that is called the Claisen condensation reaction. And this is simply the addition of enolates to esters. Now, we're going to see that these types of reactions undergo a slightly different path than that of aldehydes and ketones. And the main reason for this is because esters undergo addition-elimination reactions, not addition-protonation reactions. Remember, we've seen lots of reactions of ketones and aldehydes where a nucleophile adds irreversibly, and then you get protonation to result in alcohols. But esters are a different story. They undergo addition, and they possibly can undergo elimination reactions to give carboxylic acid derivatives. And this reactivity holds with enolates as well. So we're going to see that the outcome, the product formation, is going to be a little bit different and a little bit more challenging to see relative to that of aldehydes and ketones because something is coming off right away. So let's take a look at the first kind of type of Claisen type condensation reaction, and that's when esters react with ketone enolate. So we're forming an enolate from a ketone and then reacting it with an ester. And if we look at a very basic reaction where we have ethyl acetate reacting with acetone and adding sodium ethoxide followed by acidic conditions. Now we're going to talk about why we have to have that second step in just a little bit. But from a reactivity standpoint, we know that esters have higher pKa's than ketones and aldehydes. So ethyl acetate has a pKa of about 24 versus acetone, which has a pKa of about 17. So when I add sodium ethoxide, the first thing that's going to happen is I'm going to deprotonate acetone in this case, or my ketone in general, to form the enolate of that ketone. Now that enolate can react with the ester. And the product looks like this. It is what we call a beta diketone. So let's take a look to see how that happens and why we lost that ethoxide group. So in order to do that, we have to think about the mechanism of this reaction. And of course, the first step is that my ketone, in this case acetone, is going to react with the ethoxide and undergo deprotonation to form my enolate. So here's the enolate, and now that enolate can react with my ester, ethyl acetate. It undergoes an addition reaction to give me my addition product. So notice I've chosen, to kind of distinguish the two of them just so you can kind of see where the carbons are coming from. When the alpha carbon adds to the carbonyl, I form a carbon-oxygen single bond now. So I'm forming an oxoanion, and of course the ethoxide group is still ons coming off of it, and I've now added to the alpha carbon, and the rest of the ketone is attached. So we call this a tetrahedral intermediate, a Ti intermediate, or a Ti minus intermediate. Now, as we've seen with esters, the ethoxide is a fairly good leaving group, and therefore I can reform my carbonyl and kick off the ethoxide. And the result looks like this. So I get my beta diketone, and the ethoxide is coming off. Now the key for this reaction to work is, and this is important to understand, in terms of equilibrium, we actually have very little ketone enolate. We have very little formation initially of the beta diketone in terms of equilibrium. However, the when the ethoxide is present and I form my beta diketone, remember the acidity of those hydrogens increases drastically, and therefore I can remove one of those protons to form my this particular enolate, which is resonance stabilized. This is why I have to add that second step of acidifying. So once a reaction has taken place, I acidify the reaction conditions so that I can protonate that resonance stabilized carbanion to get my beta diketone. So one common way to make the ketone enolate is simply using a strong base like sodium amide or LDA. So one of the things that you might see is a setup that looks like this, where you're taking a ketone, you're treating it with sodium amide or LDA, followed by the treatment of an ester followed by acidification. So notice the similarities between this type of reaction and the reaction of a crossed aldol condensation, where there are a lot of similarities, right? The only difference is in that second step, instead of an ester, I could use an aldehyde. That would be a crossed aldol condensation. Here, this is a crossed Claisen condensation, where I'm taking a ketone, making the enolate, and then treating it with the ester. Now the product, again, here the product is very different than that of an aldol condensation. In an aldol condensation, I get a beta hydroxyketone or an enone. In this case, I get a beta diketone. So always remember esters form beta diketones, and the reason for that is because the alkoxide group comes off as a good leaving group. The other thing that to note is that you always have to add the last acidification step, because in all of these reactions the enolate is going to form in basic conditions, and so we have to and this is actually what drives the reaction, and so we have to acidify it. Here's another example of a ketone. Of course, in this particular example, I have only one type of alpha hydrogen, where above I had two types, but the more accessible one is going to be removed. In this one, I only have one type, so I use LDA to form the enolate. It reacts with an ester, and then upon acidification, I get this beta diketone. And so, one of the things that you'll need to work on is how do you put these structures together? What's happening? Draw out the enolate, show the enolate attacking the ester, and then make sure that your connectivity is correct. Always count your carbons. Very important, right? To count your carbons. Now, the classic Claisen condensation is when esters react with ester enolates, not ketone enolates. And in this particular example, I would say this mirrors that of an aldol condensation more appropriately, because here we're taking an ester and simply reacting it with a base. And again, the base that we use is related to the alkyl group of our ester. So if we have ethyl acetate or an ethyl ester, we're going to use sodium ethoxide. If we have a methyl ester, we're going to use sodium ethoxide, and so on and so forth. Now, when these two things react, we're going to form our ester enolate. And of course, we're also going to get ethanol if we're using sodium ethoxide as our base. And if we compare this to this type of reaction, equilibrium acid-base reaction, to that of an aldol equilibrium acid-base reaction initially, we see that we know the pK of esters is much higher than that of aldehydes, around 24, and we know that the pKa of ethanol is about 17. So there's a difference of about 7 pKa units, which means that the K is 10 to the minus 7th. And so in reality here, our equilibrium is highly favored toward the starting material, and there is actually very little enolate that's present in that solution. However, there doesn't need to be a lot of enolate present, because as soon as that enolate's formed, we know we create a good nucleophile. And therefore, that nucleophile enolate is going to react with the electrophile ester. And we get addition to occur, and our product formation is again, make sure you understand. I always draw the ester carbon skeleton first. So I have a methyl group attached to the carbon, which is now an O minus. There is an ethoxide group attached to it, and so now I add the alpha carbon, and so attached to that alpha carbon is the rest of the ester, the carbonyl with the O CH2CH3 coming off of it. This is my Ti tetrahedral minus intermediate. And of course, now this Ti intermediate, just like we saw with the addition of ketone enolate to an ester, is going to undergo elimination. So we eliminate the ethoxide, and we generate our beta keto ester, a beta keto ester. And of course, ethoxide is generated as well. So notice if I use one equivalent of ethoxide, initially it gets consumed to form the enolate. I get another equivalent of ethoxide that comes off, but now that second equivalent of ethoxide that is produced in the reaction from the loss of the loss of ethoxide from my ester can be treated as a base, and I can remove that alpha hydrogen that's much more acidic than our typical esters. And so this is going to drive the reaction forward because of the acidity of these beta keto esters. Now we have pK that's around 13, and so we have 4 pK units on that are favoring the product formation. And this is what we sometimes refer to as a chemical sinkhole. Initially, we don't have, the reaction isn't favored, or product isn't favored kinetically, but because we can get deprotonation, and now this the product of the resulting product of this reaction, the resonance stabilized anion, is favored, we can drive the reaction to product formation. So that's important to understand. Number one, we have this resonance stabilized anion that is formed at the end, and two, that once deprotonation to form that anion occurs, we generate ethanol. And therefore, if I use only one equivalent of sodium ethoxide, the ethoxide is consumed completely. And at the end of that reaction, I have neutral conditions, and the reaction stops there. Now, of course, we don't want the anion, and so we want the neutral species, and therefore we have to follow this up again through acidification. So we treat that anion with an acid, could be sulfuric acid in water, hydrochloric acid in water, some dilute acidic aqueous conditions typically, and we can get our protonation to occur and formation of our neutral product. And this is how this particular structure is called ethyl acetoacetate, and this is how we make these acetoacetate compounds that we've already seen how to use, right? We've seen these types of structures in alkylation reactions. Well, now we know how to make them. You can make ethyl acetoacetate from ethyl acetate, simply treating it with sodium ethoxide. So let's look at a couple of examples. Here we have an ester. Again, we're treating it with sodium ethoxide in ethanol, followed by that aqueous acidic workup, and the product looks like this. So it is a beta keto ester. So when this is a typical Claisen condensation reaction. Claisen condensation reactions yield beta keto esters. Important to understand that. Um, and important to distinguish between reacting a ketone, or the enolate of a ketone with an ester, and the enolate of an ester with an ester. So um, reacting ketone enolates with esters give you beta diketones. Reacting esters with enolates of esters gives you beta keto esters. And here's another reaction where I have now a methyl ester. I'm simply showing you a methyl ester. And of course, we're going to use sodium methoxide in methanol, followed by that aqueous acidic workup to generate our fairly complex beta keto, methyl beta keto ester. All right, so that sums up Claisen condensations, and we're going to see now some modifications of those Claisen condensations, but this is a typical Claisen condensation reacting an ester in basic conditions to produce beta keto esters. And if you look at these structures, you can see we can do other things with them. Since we do have that ester, we can hydrolyze it to make a carboxylic acid, which gives you a beta keto carboxylic acid, and so you can then decarboxylate that carboxylic acid to make ketones. We'll see that kind of play out in just a little bit.